Good afternoon. My talk is on our progress towards a proof of concept memory-powered heat engine. It's actually somewhat similar to a lot of the talks so far today, which has been quite nice. But yeah, I'll talk about something which might be slightly new to most of you. So a quick review of a classical heat engine. The font's funny, but that's okay. So a classical heat engine, as we all know, has two heat baths, low entropy reservoirs, and you usually the heat engine to extract some of the heat energy from the hot bath into work, but also paying some of that heat energy into the cold bath in order to increase entropy of your overall system. And this reduces the efficiency of a classical heat engine, something that we, likely all know. This leads to a typical heat engine is something you would have seen, 4 strokes following a path on a PV diagram like this, where the work extracted is the area between all the curves. For maximum efficiency for these classical heat engines, such as the Carnot cycle, it takes an infinite time to traverse the isothermal paths, or you need a ideal heat bath, so either maximum infinite temperature hot bath or a 0 temperature cold bath. So that's just a really quick review. But anyway, this cost, paying this heat energy into your cold bath reduces your efficiency, and even at the maximum efficiency limit, at the Carnot limit, you get a non 100% efficiency engine cycle. But the power output as well is 0 because of that infinite time on the isothermal paths. At maximum power, you get a fraction of that efficiency. So this is the ongoing problem of power versus efficiency in heat engines. So we are now asking ourselves, can we use quantum mechanics to overcome this classical Carnot efficiency limit while producing usable work, so something that is practical? And we're going to try to do that. So that dumping of heat energy into the cold reservoirs is the cost of paying for entropy increase. But we all accept Launder's principle, but there is another framework, which is that energy isn't the only thing that we can pay entropy with. We can pay it with other conserved quantities. And we're going to try to show that using ions. So ions are good because we have high control of the ion's internal states. They're good quantum systems generally, and we have control of heating, cooling, and potentially scalable. This might make people feel itchy with the whole you paying with other conserved quantities other than energy. There is no free lunch still. We're not extracting more energy than exists. There's still a cost of increasing entropy in the system. So I'll point it out as we go through. So the quantum memory-powered heat engine. So in the ideal case, you want to have a heat bath with heat energy, and you extract all that energy as work. And then we still need to pay for that entropy cost, that entropy increase. And we're hoping to do that using what is effectively a spin work. So it's spin labor is the term for it, which is the spin equivalent of work. And the heat engine uses that low entropy spin and converts it into a spin equivalent of thermal energy and dumps it into a spin bath. So we're still paying for the entropy increase, but now we're using spin angular momentum rather than heat energy. And in principle, this is 100% energy efficient, and we'll go through when it's actually not. But it's also 0% spin efficient. So that's kind of the big distinction. We're not getting any usability out of this spin reservoir, really. So this sort of follows a similar diagram to the PV diagram, but it's 2 entropy baths and a heat bath, and I'll come back to what this simulation comes from. So in the ideal model, we have an ion with a 3-level lambda system, 2 NED degenerate ground states, and 1 excited state. The ion's motion is trapped. The ion is trapped in a quadratic potential with its motion thermally distributed. We can then couple the motion and the spin states using a Raman pulse, where you detune the lasers such that both of them are tuned from the excited state, and then one of them is attuned by a little bit extra, where delta is a integer multiple of the vibrational frequencies. What this means is that, so this is a 2-photon process, so hopefully people know what a Raman transition is. So there's an output photon that gets stimulatedly emitted at omega 2, and it's the work photon. It carries away that little bit of extra energy, delta. So looking at in terms of entropy, so this starts off in a low entropy spin state and a high entropy motional state. And then after Raman cooling, or Raman sideband cooling, it leaves us in a lower entropy motion and a higher entropy spin. So it does this like entropy transfer from the motion to the spin states. The theory says to then introduce a spin polarized reservoir, so something like a spin polarized gas, which is already pre-prepared or just exists naturally. Upon collisions with the ion, it resets the spin with no energy cost, only if the spin states are energy degenerate. And so we've now been left with a low entropy spin and motion ion, and we can let it reheat to reset the cycle. So that's why we get this diagram of going from a hot ion and going across to a high entropy spin, and you do a follow that path, basically. How we're doing this experimentally is using a ytterbium-171 ion. So this is its overall energy level structure. This is our main cooling transition, the 370 nanometer transition. There's some leakage into the D states, which we really quickly repump back into the cooling transitions using a 935 laser. And we also have control over all the sidebands for the hyperfine splitting. This is our main transition. In particular, the MF plus or minus 1 states are the lambda system in the ideal model. We're doing this in a chip trap, which is where we can trap single ions of ytterbium, shuttle them, and expose them to lasers and other quantum operations, and potentially also trap multiple ions into chains. Our main experimental things that we want to do to show this proof of concept is to first show that a single bit of entropy transfer from the motional states into the spin states. So we can do that by doing Raman sideband cooling, which cools the ion hopefully down to the ground state or close to it, which in terms of entropy lowers the entropy down to a minimum. Then we do Raman spectrum to calculate the actual entropy left in the motional states. Then we do a state preparation or a spin state preparation into the MF equals plus 1 state. So this leaves the ion in a low entropy motion and spin. And then we let it rethermalize, so the motional modes can regather some entropy into its into the thermal bath. And then we do Raman cooling again, which transfers that entropy back into the spin states, and we can do state tomography to read out the actual entropy transferred. So the hope is that we'll be able to measure that single bit of entropy transfer between the two baths. The other thing we want to show is the efficiency of the work photon, which is where we have a single scattering event. Spontaneously emitted photons come off, and some of those will be high energy photons. They cool the ion slightly. By the way, on average, this does nothing in terms of heating or cooling. Anyway, we then couple those fibers, that light into a fiber, and pass it into a sub-megahertz fiber pro, which Rose, one of my colleagues, is working on, and she'll have a talk on Friday. And that will hopefully measure the actual work or the efficiency of that work photon, that conversion of heat energy into work. So these two experiments, they, in terms of this diagram, fulfill sort of that part of the diagram and this part of the diagram. There's a little part here which is supposed to be the dumping that entropy into a spin reservoir to reset the internal states of the heat engine. So yeah, again, as a reminder, that was done using a spin reservoir, but we just can't do that using our trap because we are operate under a ultra high vacuum, so we just can't introduce a gas. But there's kind of an argument to make that the spin states themselves are a spin reservoir. So the ion, which initially is in a low entropy spin state and a high entropy motion, you interact a laser pulse. It's left in a low entropy motion and a high entropy spin. So there's no reason to have introduced necessarily an extra layer of gas. You could think of it as like, think into the future, a gas of already pre-aligned atoms, and then do the Raman pulse, and you get it. And you replace the that thing. So in other words, this is our heat bath. The motion of the ions is the heat bath, and the spin states are the spin bath. And we basically all we're doing is it's a reversible process, by the way. So all we're doing is just transferring entropy from the motion to the spin. In doing so, we extract some work. But once the entropy is the entropy in the spin states is maximized, we can no longer use this ion, and we would have to dump it, sort of thing, unless you can extract it out using no energy. Thank you. That's all.
Is different from magnetocaloric effects, basically magnetic refrigeration, right? So your spin system is the magnetic material, the ferromagnet. What you do in magnetic refrigeration is that you apply magnetic field, you decrease the entropy in the magnetic solid, and then the system starts absorbing heat from the environment, and instead of heating up, the spins get disordered and the entropy increases. So it's basically the same thing, right?
Yes, except we're able to use that work, that photon comes out.
I understand the work part.
Right.
And of course, if you cool down, if you refrigerate the material, you can always use it as a cold source for another Carnot engine.
Right. Yeah.
And in that case, this is basically magnetic refrigeration. Right?
Yeah. So the work comes out with that extra photon. So you have that Raman pulse has it's a 2-photon process. So you have 1 photon basically come in, which absorbs at with less energy, and the second photon that you put in, and that second photon stimulates once it's excited, stimulates a photon into that mode at omega 2. So you're basically just you're basically exciting the atom and telling it to go into that transition, which is a higher energy than what you put in initially. So you get 2 photons out, which you get that photon out at the higher energy. It's a coherent process, sort of thing. And if you absorb that photon, really efficiently, that's your energy that you just extracted, the work.
Yeah, it would be really nice to see the connection with magnetocaloric effect.
Yeah, well, it is. So if you're looking at it in terms of how you take your spin reservoir, is it right that you got your magnetic thing that's already polarized, and then you cool it?
Polarize it with the magnetic field.
Right. Yeah. That is.
It was discovered in 1881.
Yeah. No, it's still doing as polarized. Yeah.